Now, the statistics we've just looked at were of an inferential nature. That means we can infer if there is a difference between two groups. And we can infer the magnitude of the significance of the result. They're described as inferential statistics. They give us a p-value of the significance of the result in numerical, quantifiable terms. But very often we take raw data and we use descriptive statistics. These just describe the data. Now, the raw data could just be a mass of numbers, it could be anything. So what we need to do is to describe that data to make it more intelligible. These are called descriptive statistics as opposed to inferential statistics. So inferential statistics, we can infer a difference and the magnitude of a significance. Descriptive statistics, we just describe the data that we've got to make it more intelligible. And the first example I want to look at is this one. Descriptive statistics, measures of central tendency. First thing I want to look at. And the first one I'm sure you've heard of before. It's simply taking averages, calculating the arithmetical mean. What is the mean figure? What is the average figure? And this is quite simple to do. So for example, here is the question. Find the mean of. So our job is to find the mean of this data set. So we've got 15, 17, 13, 14, 19, 14, 5 and 2. What is the mean, or what is the average figure of that data set? Well, all we do is we add the numbers together. Add all these together. And then we divide by the number of numbers in the set. Now, I'm going to use a calculator for this. You're welcome to do the same if you want. So all I'm going to do is add these numbers up. So I've got 15 plus 17 plus 13 plus 14 plus 19 plus 14 plus 5 plus 2 equals, and I see that that equals 99. So I've added all these numbers up together and I've found that they equal 99. And to get the average, all I'm going to do is divide that total, that 99, by the number of figures I have to begin with, which is 1, 2, 3, 4, 5, 6, 7, 8. So 99 divided by 8 equals, well, it's 12.375. I think we'll call that 12.4. So we've found the average figure, 12.4. Fairly straightforward. Add up all the numbers you've got, divide that number by the number of numbers you have, and that gives you the mean. The next figure I want to look at is the next statistic I want to look at is the median. The median value. Now, median is the value at which half the measurements in a sample lie below and which the other half lie above. The value at which half the measurements in a sample lie below and the other half lie above. So here's the question, find the median of. Find the median of these figures. Well, actually, I'm a bit stuck now, actually. Oh no, wait a minute. There's a hint here. Hint. Try making up a line plot first. So I'm going to try and make up a line plot. And in a line plot, all you do is you take the lowest numbers first and you order the numbers that you have. So let's look for the lowest number here. Well, I see the lowest number is 2.1. The next lowest here is 13.2. The next lowest after that is 14. The next next lowest after that is 14.9. The next lowest after that is 15.3. After that it's 17.8. After that it's 19.7. Then 19.9. And then the highest figure there is 21. Now I want to find out the value at which half the measurements in the sample lie below and the other half lie above. So what I'm going to do is cross out the lowest number and the highest, the second lowest and the second highest, the third lowest and the third highest, fourth lowest and the fourth highest. Now this has worked out quite well actually, because there's just one number here, 15.3. So 15.3 is the value at which half the measurements in this sample lie above and half lie below. Sorry, these are all below, these are all above. So the median in this case is 15.3. Now that median we worked out quite nicely because there was an odd number of samples. But sometimes you'll have an even number. So if you have an even number of measurements, take the mean of the two middle values. So here we have the problem, find the median of, and we've got these values. So again, we'll make a line plot. So let's start off with the lowest value, 2.1. And then the next value after that is 12. And the next one after that is 13.2. The next value after that is 14. Then 14.9, then 14.97, then after that it's 15.3, and after that it's 19.7, 19.9, and finally 21. So again, we're going to cross off the lowest and the highest, second lowest, second highest, third lowest, third highest, fourth lowest, fourth highest. And yes, it seems here we've got two measurements in the middle. So all we do in this case is we take the mean of these two figures. So it's 14.9 plus 14.97, that equals 29.87. There's two samples, so we divide by 2. And that gives us a mean of 14.935. Therefore, the median of this set of measurements is the average of the two middle ones, and that gives us 14.935, the median value. Now, so far we've looked at mean and median. The third aspect of central tendency we're going to look at is a value called the mode. So the mode, simply the mode means the result that occurs most often. The result that occurs most often. And sometimes this can tell us more than the mean. So what is the mean number of legs owned by humans in the UK? What is the mean number of legs owned by humans in the UK? Well, a few people have only got one leg, and I suppose a few very unfortunate people haven't got any at all. But most people have two. But the very fact that there's a few who have got less than two means that the mean is going to be reduced. So I don't know what this figure is, but it's probably 1.9 something, 1.98 or something like that. Of course, tragically, in some countries, the mean would be less, where for various reasons there have been a lot of traumatic amputations. But looking at the UK population, it wouldn't tell you a lot to say that the mean number of legs is 1.98. So what we do is look at the mode, the result that occurs most often. And the question we have here is find the mode of the following data. What is the mode? Well, it simply means find the number that occurs most often. So let me just have a look. 12, 15.3, 17.8, 3, 13.2, 14, 12, 14.9, 19.7, 2.1, 14.97, 21. Well, looking at that, the only number that occurs more than once is 12. There's a 12.0 there, and there's a 12.0 there. So in this set of data, the result that occurs most often is 12. Therefore, the mode of this set of data is 12. So we've looked at three measures of central tendency. The next type of descriptive statistic I want to consider is data dispersal. How is the data dispersed? So we're looking at data dispersal. This describes the range of the results, or the correct term, the scatter of the data. But the first way of describing this I simply want to look at is called the range. The range is the range between the highest measurement to the lowest measurement, or the lowest measurement to the highest measurement. What is the range of the data? So the question is, find the range of the following data. So I have a set of data here. Find the range. Now let me just look for the lowest number. Well, I see the lowest number here is 1. Now let me look for the highest number. Well, the highest number here is 99. So the range of this data is simply 1 to 99. 1 to 99. The data ranges between these two values. Right, find the range of the following data. There's another question here. What is the range of this data? Well, the lowest number here is, the lowest number I can see there is 44. And the highest number I can see there is 60. So this data ranges from 44 to 60. So the range is an aspect of data dispersal, and the range simply describes the area or the range that the data covers or ranges over. Now, using the same data, we've been set a further problem here. Calculate the mean of data sets A and B. That is, data sets A and B. What is the mean of those data sets? Well, if you actually work it out, sample A has a mean of 48.3. and sample B has a mean of 51. So the means are fairly similar. Now the next question is, does the mean indicate how dispersed the data is? Does the mean indicate the dispersal of the data? Well, I think you can see that with data set A, there's a large range, and with data set B, there's a relatively small range. And yet the means are almost the same. So data set A, large range, mean round about 50. Data set B, small range, but mean round about 50. So can you see that the mean is not telling us how widely dispersed the data is from the mean? So what we need is another descriptive statistic that will give us a kind of average distance from the mean of each point of data. How dispersed is the data? How far away is the average piece of data from the mean? Because if we knew that, the mean would mean more, because we'd know most of the numbers were close to the mean, or most of the numbers were far away from the mean. And to do this, we use a descriptive statistic referred to as standard deviation. So this term standard deviation, it's a measure of the distribution around the mean. How are data points distributed around the mean of that data set? Now, if there's no difference between the values in a set, the standard deviation will be 0. So if all the values in a data set were 6, it would be, a standard deviation would be 0. If all the values were 92, the standard deviation would be 0. Because there'd be 92 would be the number of all the components of the data set. That would also be the mean. There would be no deviation from the mean, so the standard deviation would be 0. But as the variation from the mean increases, so does the standard deviation. So in data set A, there was quite a lot of variation from the mean. In data set B, there was relatively little variation from the mean. So if we actually look at complete statistics now on sample A and sample B. So sample A, remember, had the range of 1 to 99, and sample B had the range of 44 to 58. Well, we looked at the mean, and we saw the means of these data were fairly similar. So it didn't tell us that much about it really, other than the average value. But the range, well, that tells us a bit more, because the range we knew was 1 to 99 in sample A, and the range was only 44 to 58 in sample B. So sample A was more dispersed, sample B was more tightly clustered. Now, the standard deviation is actually a statistical test that can be worked out. These days, people often do it on computers, but you can learn to work it out yourself. It's not that difficult. And for sample A, because a lot of the data were a long way away from the mean, the standard deviation was very high at 47.9. Whereas for sample B, because most of the values were fairly close to the mean, that means the average distance from the mean was relatively small. That means the standard deviation was therefore relatively small. Well, the standard deviation here was 5.1. Both of the samples had the same n. The same n equals the number in the sample. That is all it means. Both had a value of n equals 10. So it's normal to present the mean, the range, the standard deviation, and the number for any data set. This is absolutely standard in descriptive statistics. the researcher should give the mean, the range, the standard deviation and the number. Now if this is done, then that's good descriptive statistics. If any of these are missing, then the research could be criticised on those grounds because it's not giving you the information you need to assess the attributes that you'd like to assess of the particular data set. Now the next aspect of descriptive statistics I want to talk about is graphs, charting things on graphs or charts. And the first is a very simple example just to get us thinking about this. All we've got here is a plot of Tim's height. So this scale here is Tim's height in centimetres. And this is Tim's age in years along here. So Tim's height, 0, 50, 100 centimetres. Tim's age in years, 0, 1, 2, 3, 4, 5, 6 years. And here we have data plots taken every year. So when Tim was about just over 2, when he was about that height there, 60 or so centimetres. But it's interesting, these graphs you would think would be completely mathematical and scientific, but actually it's quite easy for someone who's good at manipulating data to give a particular impression that you might want to give. So if we look at the shape of that line there, well, it looks like a fairly gentle line, doesn't it? But on this graph below we have exactly the same data, and the line looks fairly steep in this case. So we have a fairly shallow line in this one and a fairly steep line in this one. But actually, if we look at it carefully, let's just pan in on this. We can see this scale here. Well, whereas that one began at 0, this one begins at 70. So this is 70, 80, 90, 100. This is a much more detailed scale. So it gives us a steeper line. Now it's quite nice because we can see things more accurately. We can work out more accurately what a particular, just over 2, what a particular height was, which is nice. But overall, in graphs, impression is quite important. And here we get the impression of a steeper line, so we get the impression here that Tim has grown more quickly than he has on the other one, which of course isn't the case, it's just the way the data is presented. So when you look at graphs, straight away always look at the scale and see what the scales are representing, and that can help you to get more information about the graph and to understand more fully the data that the graphic is actually presenting in this descriptive form. Now the next type of descriptive statistic I want to look at are trend studies. Trend studies. These show trends over a period of time. Now this red line here represents sales of the drug thalidomide. And before people knew it was dangerous to give thalidomide in pregnancy, it was given as an antiemetic in pregnancy to prevent sickness. And this red line here shows thalidomide sales 1959, 1960, 1961, 1962. And here we see the rise in thalidomide sales. Now this black line here shows the incidence of thalidomide type deformities, birth defects, and there were some appalling birth defects as a result of this drug, before people realised that this red line here was causing this black line here. In other words, that it was the thalidomide that was causing the deformity. So there's a gap here of about as you would expect, of about 9 months for the period of pregnancy. And we see that the trend in thalidomide sales is mirrored a short time later by the trend in thalidomide type birth deformities. Then when the thalidomide sales went back down to normal, well, fortunately the thalidomide type birth defects went back down to normal. Now, this example is thalidomide, but there's many other examples of trends. Now, a classic example is in the United Kingdom. Over the past 30 or 40 years, there have been more and more women starting to smoke, young girls starting to smoke, maturing into older women. Now, what we're seeing now, 20 or 30 years later, is a proportionate increase in the incidence of bronchogenic carcinomas, lung cancer, as a result of that smoking. It's just that the time gap is greater because of the latency period. So the smoking occurred 25 years ago, the amount of smoking started to increase, and now, 25 years later, well, the incidence of bronchogenic lung cancer is starting to increase as well. So we're looking at one trend and matching that with another trend. Very useful trend studies. Now, this sort of graphic shows what we call a frequency count. And the frequency count has been converted into a normal bar chart. Now, this particular case is looking at 12 workers. Worker 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this scale is showing how many days sickness they lost in a particular year. So that's 0. I guess 5 had come in about there. 15 had come in about there. So worker 1, it looks like worker 1 lost 1 day maybe from sickness. Worker 2 lost, that looks probably like 3 days. Worker 3 lost about 7 days. Worker 4, dear me, they lost 20 days from sickness. So a frequency count is looking at, is putting people or results into particular categories. In this case, each category is a single worker, and working out how many times a particular thing we're measuring falls into that category. So frequency count, normally expressed as a bar chart, something like this. Now, this is another frequency count here. Here we have a case number. In this case, it's number of children. 1, 2, 3, 4, 5, 6, 7. 7 children. And variable 1 here are percentage figures. So this is 0%, 10%, 20%, and 30%. And it's the percentage of ice cream eaten per child. So of the total amount of ice cream consumed, child 1 ate 12% of the total amount of ice cream consumed. 12%. Child 2, well, child 2 ate 27% of the total amount of ice cream consumed. Child 4 only ate 7% of the total amount of ice cream consumed. Now, here is exactly the same information, but this time it's displayed in a pie chart. It's like a cake, and we're looking at the size of the slice of cake that represents an individual variable. And again, this is percentage of ice cream consumed per child. It's the same information, but given as a pie chart. So this child ate 27%, this child ate 21%, this child 7%, this child 8%, this child 19%, this child 6%. So the same data as we've just shown in the bar chart, still a type of frequency count, but this time shown as a pie chart.